So in the last lecture, we looked at polymers, that is these kind of long growing chains of the same sort of unit repeating over and over again. If you recall, we had just a long chain of carbon and then some R groups kind of hanging off the sides. And then as the numbers of molecules in a typical chemistry experiment are typically on the orders of trillions and, well, not even, or much greater than trillions, we had to start thinking about alternative depictions of the structure. So polymer, we have this joke like the bond line structure of a polymer is just a spaghetti noodle. Whoop. All right, so it's just this kind of long chain because the length of the molecule greatly is much greater than the small bits of differential structure that occur across each of the atoms. So drawing like a typical zigzag structure is just impractical to actually get the scale of the overall molecule. So what we can do instead is consider an alternative way of depicting these large molecules. But before we get into that, let's just mention some brief basics. First, I will say a polymer. This is broken down into kind of poly meaning many, and then mer meaning things. So polymer means many things. This is in contrast to monomer. Monomer is mono for single and mer for our things. Okay, so polymers are large molecules made by the repeated attachment of monomers. Okay, so monomers, that's why I wanted to get that word out in front of us. Monomers are kind of these single things. We take monomers and we assemble them one after another into a long chain, and that long chain is called a polymer. So this monomer is usually a typical, I'll use typical kind of in quotes, a typical organic molecule. So these sorts of things you can draw as they're typical organic molecules, we can have typical structural depictions. So examples are practical to consider. We've got our alkenes. This is what we used yesterday. We've got amino acids. And then, gosh, there are so many. I'm just trying to think of, we'll just go with these two, alkenes and amino acids. So when alkenes polymerize and form polymers, they usually form polyvinyl polymers. Whereas amino acids are a class of biological monomers that form biological polymers or biomacromolecules in some cases. Amino acids in particular make proteins, which are often called polypeptide, named after the attachment point between the amino acids, which is called the peptide bond. It's just an amide, just between us. Okay, anyway, so polyvinyl polymers are what I want to focus on at this point in the semester. So polyvinyl polymers result from polymerization of vinyl monomers, where polymerization is just the reaction to convert a monomer into polymers. And we talked about that reaction last time, where if we did our anti-Markovnikov hydrohalogenation with a radical initiator, but we just left the hydrohalogen source out, then the alkene would only react with itself in a growing chain. And if we assume that termination is not taking place at an appreciable level, we would actually get a growing chain up to a certain point once everything is sort of consumed. And that is the monomer building on itself to make a polymer. Okay, so we have now kind of described polyvinyl polymers, but I haven't really defined what a vinyl group is. So vinyl, this is a highly industrial name, industrial term for something attached to an alkene. And I mean, it's not just an industrial term, it's everywhere. It's just, it's more prominent in industry. So if I say vinyl chloride, that's referring to an alkene having a chlorine atom. And so you could also call this chloroethene, for example, but people call it vinyl chloride. So polymerization of vinyl chloride with ROOR and heat, this is our polymerization approach for alkenes, gives rise to polyvinyl chloride, or PVC. And we can actually draw the chain like that. What we have is we have an RO group attached to the CH2, which is attached to a CH, which is attached to a chlorine. Let's map some of these atoms. So I'm going to put green here, red here, and then sure, yellow for the chlorine atom. So we have green, red, yellow. Now what we're going to do is repeat this over and over again. We now have our new bond between our monomer units. And that's going to build a chlorine atom, which is going to bond to another vinyl chloride unit. And you get this sort of arrangement. This is just like what we drew last time, but it has a chlorine atom in place of the R group. And so if we go back to our highlighting, I mean, the yellows are pretty easy to see, the chlorine atoms. But then the green, I think it is helpful to map the atom. The green are going to be the tips of our little side chain here. And then the red are the carbon atoms that are attached to our chlorine atom. So what we've done is we've taken several monomers, several vinyl chloride monomers, and polymerized them over and over again, growing chain, and we get to a molecule called polyvinyl chloride. So I have to create a new page here. Now what's great about this, as I'm creating new pages, what's great about these polymers is that they take on properties that are vastly different from their monomers. Okay, so polymers have different properties compared to their monomers. Okay, so vinyl chloride is a difficult molecule to handle because it has a low boiling point, but as soon as you polymerize it into polyvinyl chloride, which I think I said, I didn't write this out. I'm going to write PVC. PVC, or PVC piping, for example, is all of a sudden a solid that's white and is very easy to handle. Like you can saw it in half with just a hacksaw, but then it's sturdy enough to kind of hold up and you know, do some interesting things. It's water resistant for the most part, so you can flush water through it. Okay. The important thing is that new properties emerge from polymerization, products of polymerization, and we can use these to get access to materials. These properties are useful to materials, are useful in making things. That is to say, they have material properties. Like PVC is very sturdy, okay? And maybe you want something that doesn't have chlorine atoms. You can actually just take ethene and you can actually, and this is also called ethylene in industry, and you can polymerize this, the same sort of radical initiator approach, and you can get to a chain which has RO, just a bunch of carbon atoms that again gets exceedingly longer and longer and longer and longer, so that you don't even notice the RO group at the end. And this is called a polyethylene. And polyethylene has different properties compared to polyvinyl chloride. And so PE. And you can actually process these differently to get things like HDPE, which is high density polyethylene. And you could take this molecule. This molecule is acrylonitrile, because the nitrile is sort of like a nitrile is CN. Because the nitrile group, the CN, is kind of like a carbonyl. Instead of this being vinyl, it's acrylo instead. But we can take this and we can do the same polymerization on it, and we get to a polyacrylonitrile. Okay. Yeah, this can kind of keep going. And so if you hear things like vinyl, it's typically like a polymer with some sort of vinyl monomer. Now, what we want to do is be able to communicate this structural information in a way that's more easy to digest, okay? The problem is the structures are so exceedingly big. So how do we communicate the structure of polymers, or communicating / representing structural info for polymers? What we do is we establish repeat units. So we show as only the repeat unit. And then we provide other information like what's the molecular weight of the molecule, and we have to have some sort of average, because in a polymer sample, you have chains. Everything might have the same type of atoms present, but the chains will be of different length. Like most will be like right here in the middle. Some will be a little bit longer. Some will be a little bit shorter. Some will be teeny tiny, and some may even be monomers. In fact, the monomers, the new car smell is typically quite often toxic plastic monomers. And I should emphasize, polymers are plastics. Plastic monomers that we're inhaling because they're volatile organic molecules. Not great. So that new car smells a little toxic. Okay, so I'm going to capture that idea. I didn't mention that. So polymers are plastics. Maybe I'll get to that in a second. But anyway, we want to show as the repeat unit. So repeat units for polymers, this is how we like to think of them. If we have vinyl chloride, this is our monomer, and we polymerize, then it's correct that we have to think about this growing chain as a bunch of chlorines separated by a CH2 group, and that goes on forever in either direction. But we say that in this molecule, what we have is several repeat units over and over again. And maybe actually, if you highlighted that, that's fine. But I'm going to go this way so that it has the same orientation as my starting molecule. And I should have chlorine here as well. So sorry if you erase that. But this unit is repeated. Unit or segment is repeated over and over again. Repeated over and over again. Okay, so what we're going to do is we're going to just try to capture that information. So the repeat unit is shown as the atoms that are actually involved in making the molecule or making the polymer chain. That is, we have a CH2 to a CH, which has a chlorine attached to it. And I put these parentheses around the bonds extending out from the repeat unit to tell me that everything beyond the parentheses is just the same. Like this CH chlorine goes off to a CH, the CH chlorine goes off to a CH2, and so on. Like if you want me to, I can just indicate that here. But this isn't the stuff we want to write. This isn't the stuff we want to capture. The only thing we want to capture is the thing in parentheses. And so what I also do is I put a little n here that tells me that this is repeated n times. N is just some number. So it could be 100, which means that repeat unit is repeated 100 times. It could be 1,000. Many times, when we're just showing a quick structural depiction, we just write the letter N. If we know more information about the average molecular weight of our polymer sample, then we could include a specific number there. But quite often the case, when we're just trying to communicate the structural information, we just write the letter N. So what do you want to be able to do? You need to be able to convert between monomers and repeat unit. And so it's sort of back and forth. And so what I'm saying here is if I handed you vinyl chloride and I said, draw the repeat unit of the polymer, you would then say, okay, well, I know that I need brackets here, parentheses. What I'm going to do is just draw my vinyl chloride without the double bond. Then I'm going to draw bonds from the parentheses extending into the from the outside of the parentheses into the inside of the parentheses, connecting to the group that was part of my vinyl unit. So it's the alkene that forms the backbone. The alkene carbons here and here form the backbone carbon, and then the chlorine serves as a side chain. And I can write the letter N to tell everybody that I know that's repeated N number of times. And similarly, we could work backwards from our repeat unit, Cn here. We could work backwards to a vinyl group where I just capture the fact that I've got my two carbons are the alkenes of my monomer, and then whatever is attached to them, I just include. And we can get to some more complicated structures if we wanted to. This is polymethyl methacrylate, or excuse me, this is methyl methacrylate. And so if we polymerize this, we get to polymethyl methacrylate, which has a methyl group, and then this at this position, and this is plexiglass. So I've talked about PVC and plexiglass. You can probably picture. So what's great about these things is they and you know, ethylene. I should show polyethylene as I'm saying this. What's great about these things is they have such unique properties, unique from any sort of small molecule. And we could take advantage of that to enrich and improve our lives. So polyethylene is just the two carbons, and there's nothing off the side chain because bond line structures say we don't have to add hydrogens. Okay, so back to what I was talking about. These things are useful, polymers are useful because the properties of the long chain are greatly different from the properties of the small chain. One distinct property, a property of what are called thermoset polymers, and what leads to a lot of the plastics that we use today, is that you can heat these things up, and instead of burning or igniting, what they do is melt. So you can take these long chains and heat them up, melt them, cast them into a mold, And then what you have is something that's the shape of whatever you need. That was a technique that was usually confined to things like metals only. And so if you wanted to build, I mean, think about all the plastic things in our life. If you wanted to cast the shape of, I'm looking around my desk, like a laptop charger, and you had this big metal thing, well, that would be an issue because that big metal thing would conduct electricity, and you're trying to, insulate maybe the electric current as you're trying to charge your laptop. So that could be an issue. So plastics came around, and what was nice about plastics was you didn't have to mine for the plastics like you did the metal. They were a little bit easier to cast. They didn't require as high of temperatures to get them to melt. So you'd melt them, cast them into a shape, and the shape could be so many different things. And if you had something like polyethylene, you could get to a hard, after it cooled, it could be hard and rigid. But some plastics are a little bit more softer and have some give. You have some plastics that are more resistant to water. And so like PVC, you can run water over it for a long time and you won't see the consequences of erosion. So PVC pipes last a long time. Now, these things are easier to come by than metals, than mining metals, right? And they're easier to process. Here's the issue. They're a little too easy and a little bit too easy to process, have a few too many properties, and are just too easy to come by. What that means is that if you were in the business of producing materials, plastics kind of, in the 1950s, plastics came on the scene and really took over. You didn't have to cut down trees if you wanted to make a chair. You could just get enough plastic, cast it into the shapes that you needed to build your chair. Now, when plastics came on the scene, they were too good at everything. They became too good at everything and they dominated the industry. They've improved our lives tremendously, it's true, but I would argue they were so cheap, they really pushed everything out of the way to make room for a plastics industry. And I'm sure you're all well aware that just plastics are too good at their job. They're too durable and they were too cheap. We use them in everything, and they were so good at being durable and so cheap. We had so many single-use items that we couldn't dispose of because we didn't know how to get rid of the plastic. It was too resistant to water breakdown. And now we've got plastic floating around the ocean making islands because we didn't know what to do with it when we threw it away. And it's just such a big part of our lives now. And these things are just so cheap, it's kind of hard to move on to a new, more renewable technology. Now, additionally, fundamentally, plastics derive from the molecules that I've drawn today. And these molecules are interesting and important to study, but it's important to note all of these molecules are derived from petroleum sources. Now, I think that's an issue. We have to move away from our dependence on these types of products, particularly in the future, and look for more sustainable options. So not only are we not able to get rid of these things, not only is there not an economic benefit to getting rid of these things, for which kind of stifles innovation if you don't have money behind it, like if everybody's like, it's just cheaper to use plastics. The other thing is fundamentally our source for these plastics is fossil fuels, our fossil fuels. And so the processing of them requires the continued processing and practice of techniques that ultimately lead to more of the things that lead to climate change and an unsustainable future. So one thing that we have to keep in mind is as useful as plastics are, and they're incredibly useful. I mean, think about all the different shapes and all the different properties. Some you can see through, some are just ultra hard. They can hold metals. Some can, and most can insulate electricity. They've just transformed our lives so much, but we have to make sure that we can manage them properly when we're done with them. I mean, think about how many single-use like plastic things there are out there. Okay, anyway, rant over, lecture over. We'll pick up with a brand new reaction, really exciting reaction that deals all the reaction next time.